let's start. First of all, hey everyone, I'm Slava, and we have only 30 minutes till the lunch, so let's jump directly to the conspiracy theory of the talk and figure out details later. And conspiracy theory of the day is graphs are everywhere. So first of all, what graph is? Graph is dots connected by lines. Okay, but this feels a bit childish. Let's make a bit less childish. Graphs is two sets, vertices and edges, where edges is a subset of Cartesian square vertices. Okay, cool, this is not childish, but there is an issue with C++ conference. Okay, I can do better. Graph is tasks and dependencies between them. What you can see on the screenshot is dependencies of localfs target on my systemd Linux machine. And if you are running Linux, every time when you boot, you execute in a graph of tasks. Okay, probably you could guess that talk going to be something about graphs. Let's draw where our talk is in human knowledge. So you can see a huge ellipsis, which is graph theory and applications. And there is a smaller, greener thing, which is graphs in C++. And even smaller ellipsis is in process graph of tasks model. This means that we are going to have a binary, and inside of that we are going to have tasks, and there are going to be dependency between them. And the small red bleep is my talk. Cool. Before we actually approach, a few disclaimers. First of all, the talk is based on my journey. That's why it's infinitely incomplete and biased towards what I have seen. And code quality is limited by size of the slide. And if you see something clumsy, there are two options. I did nasty work, or I really tried to fit it into one slide. Both are equivalent. Okay, so disclaimers are done. Let's try to understand why graphs. First of all, it's nice abstraction. You can structure your code by tasks. So you can have a class or function per vertex, and it's infinitely structure your code somehow reasonably. And the second stuff which we really like as C++ engineer, it has built-in parallelism. If you have, like, what is drawn on the slide? We have a finished task and two executing tasks dependent on this done task, and some task is waiting which is dependent on executing tasks. If you don't have dependency between two tasks, they can be executed in parallel. And the second one usually bring this model to lots of applications. Okay, these two actually large enough to meet this abstraction in gazillion different branches of engineering. Now let's try to understand the portrait of our client. First of all, as I said, we are talking about in-process or in-memory stuff. So it's going to be C++ binary or library, which is developed by a large team. And this is really important point for us, because by chance I was working in large teams for all my career, and most of the problems we are going to solve pops up only in large team. And obviously with task and dependencies between them inside, because it's the topic of the talk. And all the talk we are going to implement something around these tasks and dependencies, and we are going to have the following requirements. Code is readable. If you have a large team and your code is not readable, so you can do mostly anything, you can progress. And reasonably performant. It's important that this is the second stuff. We are not going to count L1 cache misses or virtual calls or whatever. We just need something reasonable in C++. And as we're in a large team, big focus going to be on ease of add task and dependencies between them. And apart of those simple ones, there could be a gazillions of domain-specific requirements. Let's go through them. We may want granular control over threading model, means which task executed on which thread. There could be condition on the edges, like if some task returns some result, we want to execute this dependency, otherwise another one. Async operations in tasks, and this is kind of popular. Sometimes you want to make an RPC or network request from the task, and you don't want to block a thread of your application on it. And this requires some hassle from the abstractions we are going to bring. Data transfer through edges, streaming of partial results, cycles, all this kind of stuff pops up when you actually bring in this to your application, but we briefly discuss it. Okay, and now we are jumping to what options we actually have now. So like what you can meet in at least 10 years application which is developed by 50 people. And there is a tiny small text which you can't read. We are skipping trivial approaches and jumping directly to juicy parts. In trivial approaches, somehow leaving callbacks because they are so old, so not interested, and they're impossible to maintain. So if you had a, doesn't matter. So and the first thing which comes to mind when you're thinking about, okay, I have tasks, I have dependencies, is C++11 futures, and this is old enough thingy, and before C++11 it existed in gazillion libraries, and this is a native idea to think, okay, I can do everything with futures. Short recap, what future is. We have a promise, stored promise object where you can put a value, you can get a future from it as an object on which you can wait, and after that you can spawn a thread. Here we're putting our promise to this, to the closure of lambda, which is going to be executed in this thread. After that we can wait, and after that we can output result. Waiting, we are on future. Okay, cool, everything simple. But to implement a graph of tasks model, we need a bit more. It's organically that more than one thing going to wait on for some data, for some task to finish. Okay, recap a bit longer. The same thing, promise, where we're going to set a value, and after that shared future pops up, and shared future in opposed to stored future is copyable object. While usual future is move only, and this SS is move only on one object and wait on it. And after that we spawn two threads. Both of them are waiting on the future, and in the end we are setting value and returning result. Okay, breathe in, breathe out. A few more seconds to stare on slide and the problem of the slide. So we can notice that T first and T second are not synchronized, and we easily can get this thingy. Okay, let's fix it. So we will add another promise, which is going to be void in our case. So we're not passing any value through future. So it's going to be just void, just for synchronization. We are passing future, in our case just regular future, to the capture of the second thread, and we are waiting on it, and we are moving progress to the first thread, and after that in the end we are setting the value, and the rest of the stuff is as before. Okay, now we have synchronization between thread second and thread first, and we are getting expected output which we really wanted to get. Okay, cool, but oops, seems like we did a graph. If you think a bit, we have the following dependencies. We have a thread 1, thread 2. There is a dependency between them by f1 wait. And both of them are dependent on main thread by future wait. Okay, so this is already complicated enough picture to try to generalize this story. Now let's try to make something you could met in a production code, close to production code, with these abstractions. So actually gazillions of ways to do so. I am not plagiarizing, but mimic one of application I met in my life some years ago. Let's implement an interface per every task. And the interface is going to be quite straightforward. We are going to expose the alias for the future type. And we are going to have two methods. GetFuture, which allows you to wait for this task, and a method run, which is actually doing some work. And implementation of an awesome task is going to be kind of straightforward. We are inferred from our interface. We are storing two future dependencies which we need. And after that, we are storing our promise and copy of our future. Constructor is straightforward. We just need to get future from to our dependencies interfaces. And get future going to return a copy of expected future. Okay, nice. Yeah. Okay, cool. And run method going to just wait until futures, do some work, updating the result, somewhere in line 8 in the comment, do something. And after that, set value on the promise. Nice. Okay, with this approach, there is an issue who is going to execute all this stuff. So we had the method run, and I purposely made it private. Or not private, protected. So we kind of can't call it from outside, and nothing inside of our task is implementing, calling this method run. So something do not adds up. Okay, let's do an ugly fix. Let's add a thread to every task, and going to be executor thread. This executor thread going to just in constructor start and call method run, and everything going to work. Okay, cool, nice. But this is an ugly fix. Why ugly? In any production grade system in large production, you are going to have at least thousands of tasks per second. And you can't span thousands of threads per second just because you need. Let's think a bit about non-ugly fix for this story. Okay, we have something. First of all, in std experimental, which you probably don't want to use in your production code, there is a when all, which allows you to get a future on all your dependencies. So like we have dependency first, dependency second. You can call when all of them and get a future, which is going to be set once all futures are set. And after that, you can attach a continuation to your future. Okay, std experimental is too experimental to some extent. Oh, we can take boost or any other implementation. And then less ugly fix going to look like that. We are waiting for all and storing result, future result somewhere there. Actually, we're not going to use it. After that, we are adjusting our lambda and run to take the dependencies. Okay, we are done. Awesome, we have a production kind of ready framework, and there is a systems which is running for ages and something like this. Doesn't it look awesome? So everything what we need there. We have task, we have dependencies, etc. Actually, not really. At some moment, somebody will start wait only on part of dependencies, and you will get a crazy control flow when nobody in the team understand like in which order this stuff is actually executed. In a few years, once your team change the completely and everyone going to be new faces, people start fail to find on which to depend to get your data. So like which interface you should depend from which future, etc. And eventually someone will add cycler dependency, which you will find only in production because there was some condition when you wait, when you're not, and this triggered it only in a few days after the rollout. And all this created terrible situations that it's became really not easy to add the tasks and dependencies once your graph is large enough and given enough amount of people. Okay, let's try to reflect from where this problem came. Actually, I don't know, but I think that the problem starts that futures are really dependent or focused on the dependencies between stuff. You have a way to express that this thing dependent on this thing, and everyone is running around dependencies. But actually, people want to write code, not dependencies. Let's try to focus on tasks and build a framework which allows everyone who wants to implement a task just to implement a task and do not think about other stuff. Okay, focusing on task, not edges. Our target state going to be like this. We want to declare a result data type. Okay, this is organic. You want to return something, you're declaring result data type. Probably you know which data you need. So you will need to list all data types you want as input. And you want to implement a business logic, because that's what really want. After that, there is some C++ magic going to happen, and graph of tasks is ready to be executed. Cool, that is our target state for the next 10 minutes. Let's try to achieve it. And now slideware ahead. To properly implement it, it's a bit wordy. That's why I presenting a few slides of slideware. After that, I'm going to illustrate every gadget which we need with some links to Godbolt. Hopefully it works. Let's go. Slideware for a task. What is it? We have some task, and it inherited from a base task, which has result type, as we discussed, and list of dependencies. I listed dependency first, dependency second. It can be many more. Cool. After that, we want to implement one method run, which calling mysterious method get on the dependency. That could be more. After that, I'm getting get output. The difference between get and get output only constantness of the reference. And during your business logic in line 8, do something and set result, you're actually putting something to the result type. And after that, we have a triply mysterious, probably macros register task. And that's it. That is the target in terms of the code, what we want for implementers of business logic in our team. And here's some slideware for execution of the graph. So get graph for some output type and execute with some inputs. Probably your data processing pipeline needs some inputs. You will have to provide them. And this is the arguments of the execute. Okay. Careful listener now should ask two questions. Why do we need it and how to make it work? I tried to work really hard to explain why do we need it. We want to separate dependencies and execution of the graph from the implementing of the business logic. And how to make it work? This is a bit hard question, and now we are going to work to explain it. As I said, we will need a few gadgets. The first one is unexpected unique name. Somewhere inside of register task, we will need programmatically generate unique name for a variable. And we are, in an old team which is running, something relatively modern, C++ 11, for example, maybe 17, not more. And we're doing it in the old way. Unique name of some base name is going to be concatenation of base name and counter, where counter is compiler provided macros, which is incremented every time when it's substituted. And after that, here is true C style stuff, concatenate to string and expand macros. And okay, bonus point if someone can say why it's macros in direction. Anyone?
Because otherwise it just takes the thing, you need it to take the thing and then exclude.
Exactly. If I just take a underscore concat, my counter will be just a counter as a string, not expansion of a macro. Never use this stuff, or at least write once and after that never touch again. And the code is working as expected. So we declared 3 unique variables with base name foo. We generated name foo0, foo1, foo2, and initialized them by 1 to 3, and output is expected. Okay, now we are ready for the magic of link time registration. Okay, this is probably the hardest slide in the whole presentation. Let's start on it. So we have a macros register task, where task, as you remember, this is the name of our class which is going to implement our business logic. In this macros, I'm expanding to the creation of variable of type int with unique name based on the name of the type. And I initialized it, oh terrible, with the call of the lambda function in place. And this lambda function doing something like this. It's get sharp task, which is just a string. I have a name of the type, and after that I converted it to string literal with the macroses. Terrible. And after that I'm calling arbitrary code inside. Okay, we're going to do it only once in this presentation and never more. Why do I need all this crazy stuff? If you think once you link this stuff to your binary, so someone implemented a CC file, build an object file after it, and after that you are link it to your binary. you magically start executing a read to record on the, during the start of your program because you need to initialize this int. Maybe you will need to do some magic with your build system to actually link, but it's overcomable. And here you theoretically can take a global fabric and register there anything you want. A few words going to be about this later. Next gadget. So we are done with link time registration. We want to build a graph. And now, in my approach, graph represented by a type. But it's really hard to work with type in runtime. So there is runtime type information, but I heard it's not really nice, so we need something simpler. We want to exchange this type to some integer, which is easy copyable and we can operate with. And here is the draft of how to do it. The first thing, we are going to have a usual function which is going to return new ID on every call. Quite straightforward, atomic to being able to call it from different threads and do not think about it too much. And after that, I have a templated function getTypeID with type as a parameter. And it's going to be instantiated in every CC file. So we could think, OK, I have tons of instantiation. Probably I store in my line 6 different getNext IDs. But no, again, linker will do the magic, and you will get only one instantiation as a final binary. So in every place in your code where you call this getTypeID with a specific template type, you will get the same integer. OK, so now you can map a type to an int. And int is nice stuff. You can actually put it in a map and do whatever. And after that, you can use it easily. So something like this, and mostly from any CC file. And it will output, if we just do that, it's going to be 0, 1 as expected. Cool. And now let's try to bring all this stuff together. You will need a global factory, or maybe type parameterized factory, that if you want to store several graphs in your binary. You're getting it in the registration lambda. After that, you get all your task types and your result types and exchange them to int. And this int going to be, I don't know, representation of your type in the runtime. After that, you can build graph with this task and dependencies. And after that, you can execute this graph in any way you want. And those engineer who was writing this code actually may not think about how this graph is actually executed. And you need just the team of, 2, 3 engineers who are actually writing this infrastructure for you. OK, let's take a look onto the missing parts. Missing parts are those gets. OK, let's add a bit of implementation of the idea of these guys. Get. First of all, we want to provide some type safety that you can't get anything from in the task. So you're adding a static assert that type you are trying to get is actually in your dependencies. And after that, you will have a type raise storage, which is probably going to return something vulgar like void pointer or whatever, or pointer to a base classes if all your types has a common ancestor. And after that, you static cast it to the type you need. And for the user of this get function, everything going to be type safe, and all type unsafety going to be enclosed in really small piece. And you need to make it only this, carefully. OK, conclusion for this approach. This tricks allows to really separate implementation of business logic and all fancy stuff about schedulers and developing graph execution engine. And it's really work nicely in many applications. What I saw is data processing. But it requires quite a lot of hustle and sometimes a bit dark magic to make it work. And it's hard to implement all domain-specific requirements which I saw. For example, it's hard to make an async call inside of the run and not block the thread. But given modern enough C++, probably this is doable, but I haven't seen a working implementation. And the last thing about this, it's hardly composable. If you have several graphs implemented in such approach, it's hard to compose them together. You have nothing or everything. And now, okay, we spent most of the time on talking about how to make it in a large team, and now let's talk about, let me teaser about nice stuff which I haven't seen in production about how to execute graphs. And there are two awesome stuff which I want to try, but I haven't tried. This is a library task flow, which is quite well advertised and which has a sane interface as up to me. You're creating a executor, create a task flow, after that registering tasks, declaring a graph, execute, you're done. And if you put something like this beneath those tricks, you are getting a nice separation, and after that you are getting a ready-made library which will execute graph for you, and seems like, okay, you can not have any more those 3 engineers who are executing graphs for you. And obviously, I'm really waiting for P2300 proposal, which is STD execution, and about this going to be a huge series of 2 talks after the lunch. That's why I'm going to skip this thingy. STD exec is a reference implementation of this proposal. Let's make a few of conclusions. Obviously, there are more async execution libraries. And I haven't seen a library where you can easily declare a huge graph and keep it maintainable. Sender receivers hopefully will make this graph composable. And now we're ready for the final slide with all ideas we heard. First one, C++11 futures are not enough in large teams. We saw a nasty recipe of scalable in terms of people, task graph framework. Link time registration is nice tool for those framework. And I really hope that the next C++ standard will make all this topic much more composable and standardized and with less ugly tricks. Questions? Yep.
So with current C++ 20 or 23, you can't, there's no good libraries that you found that allow you to compose DAGs instead of DAGs or task dependencies?
I would say yes, because they're using quite diverse mechanisms, and as a result, you can't really easily build them together. There is a futures which meant to be so.
Assuming you use one library,
yes.
You can't have 2 teams to take multiple DAGs and connect them together.
Yep. Assuming you are using one library. Assuming you are using one library and you have a good separation between business logic and description of graph, probably you can. And that is the kind of idea of the middle of the talk. If you separate it well, after that you can put any library beneath your separation and be king. Yep.
I noticed that in declaring the task itself, it ended up becoming extremely strongly typed on the input and the output, which sounds like it would make it difficult to add a task in between 2 tasks that just say filters data as the same input and output.
No, you will need a type which will represent input and output of those guys. Yeah.
And that means that that once you have a graph and you have all the types, how do you then insert, say, a single filter of the data between 2 existing ones without having to redeclare both of those in terms of the type they
No, if you want to change a type of input of some task, you will need to actually change it.
Right. In this case, you're not changing the types. You're just adding something with the same input and output.
No, you're saying that, okay, suppose I have vector of something and something accepting this vector of something. And I want to add a filtering task which is going to be filter this. Okay, you are changing this vector of something to a new type, which is still going to be vector of something, but it's going to be a new type representing the state of the data in your system. Okay, after that you're implementing a task which accepting an old vector of data and produce a new vector of data which is represent filtered vector of data. And after that you're essentially done. You will need to create a temporary type to represent it. Okay, we are out of time. Thank you. I'm happy to answer questions.